Hey guys, welcome back to the channel. Today we'll be doing the first episode, or episode 2. We are indexing at 0, so it's episode number 1. We'll be actually going over some theory on ray tracing, theory about ray tracing. I think it's important we know the basics of how ray tracing works. So we'll be going over a very high level overview of how ray tracing works and then implementing programming, I think starting from the next episode. So let's get right into it. So what is ray tracing? Ray tracing is actually trying to mimic the actual physical process of light, right? So I have my whiteboard here. So let's say we have a happy little sun or a light source for any matter. And then we have a happy little ball, right? Now what happens in the real world is the electrons inside the sun get excited and they shoot off electrons, or photons, sorry. So the photons are the light and they travel in a straight path and they hit the object. Now when it hits the object, a couple of things can happen, right? And it's completely dependent on the object itself, and that's what we call materials. So if you're coming from any 3D program, you might have heard of materials. Even in Unreal Engine, we have materials and stuff. Now this is kind of misleading, because materials is kind of shown in the 3D programming world, or 3D artist world, I don't know how to call it, 3D design world, as a wrap, right? You have a material. So let's say this object, a mesh, right? So a mesh is kind of seen as this concrete block or made of concrete or whatnot, and then you have a wrap, like a car wrap or a paint or spray paint put on top of an object, and that is called the material, right? However, that's not true in the real world. Material actually is the physical object itself. So we have, what material are you looking for? So I'm looking for iron, right? Or glass. So the atoms itself, the molecules, the combination of molecules is actually called the materials. That's why we have material scientists and who create new materials, synthesizing stuff like that. So this ball is actually a material. It's not a mesh. Think of it that way when you're talking about real life, right? When we're coming into 3D programming, obviously it's going to be a mesh, but this object is actually the material itself. So the material is going to decide whether to absorb the light or reflect the light or refract the light. Reflection actually also has attenuation to it. So reflection actually absorbs the light itself. So let's say we have R, G and B components of the light, and this material absorbs just the G component, right? So what happens, the reflection is only going to have R and B. So this is going to turn purple. So this material is going to seem as purple, right? So whatever the thing absorbs is going to just subtract and reflect the rest of it. So that's why when you have black color, the black color material actually absorbs the entirety of the visible light spectrum. So if you have 255, 255 and 255 for the vector color, so I'm talking about the pixel range here, not the real world, it absorbs the entire range, so it reflects nothing pretty much. Now keep in mind, I'm talking about real life scenario here. When it comes to programming, we still have to reflect the light, right? So keep that in mind. We'll have to return a value somehow. It could be 0, it could be calculating colors pretty much. So let's come back to our scenario here, the real world scenario. So then we have the viewer, right? So this is us seeing into the world. What happens is we don't see all of the light the light source emits off and what bounces around, right? So this light source, let's say for this light source, is actually going to go infinitely out. We'll never see it, right? It'll get absorbed completely some point, but this light source or this light ray is going to hit this object and then bounce into our eyeballs. and that's what we see as color pretty much, right? So we'll see this as purple, and whatever bounces into our eyes we can see technically, right? And this is quite inefficient when it comes to programming, because as I mentioned before, we are not seeing every light trace and every light bounce. We might have situations where this light goes here and this light bounces back and this light bounces somewhere over here and goes there. So we have an object here, we can't bend light in the middle of air. If you could see every bounce, every direction of light, then we'll have omnidirectional vision, right? So we'll have superpowers at this point. We can see what's going on behind us, we can see what's going on in America, and I could be sitting in India. So that's why it doesn't work that way. So in computation, what happens is, let me actually erase all of this. It's getting quite messy down here, oh, right, let's just clean everything, right? So in computation, what we do is actually we do the reverse. As I mentioned, because we're not seeing all the light, we're actually wasting resources. So let's say this calculation, at the end of the day, ray tracing is just calculating the color for a pixel. So if you have 500 pixels, we have to shoot 1 pixel, so 1 ray per pixel, which is again without anti-aliasing. If you have anti-aliasing, we'll be shooting around 50-60 rays just per pixel, right? So we're shooting 1 pixel here and then it hits here. So this contributes nothing to the viewport, right? So this is the camera we're seeing through. So this is our eyes in the game engine. So game engine, render engine, anything, this is what we're seeing through. This ray actually doesn't actually contribute to the output, right? We're not seeing this result. Why would we need to calculate from the light source itself? So the same goes for a calculation like this. So it might hit here, the ray might hit here, the light, and then bounce just off the eye, so the light or the camera, right? And it's still a failed calculation because it really doesn't contribute to the overall image we see. So let's say we have 500 calculations, right? Let's say just 20% of those calculations are actually going to hit the eye. So that's just wasting 80% of resources, just like that. And there's going to be scenarios where there's going to be a block, an obstacle right in front of our eyes. So it's guaranteed no light is going to get into our eyes. But then we're still calculating from this light source. So 100% of our resources is just going to go to waste. So keep that in mind. So in order to tackle this, we just do the exact reverse, right? I'm going to come down here. I'm going to draw a happy sun again. So a happy little sun and a happy little ball, right? And we have the camera, right? That's the camera and the eye point, right? Simply. So now what we do is, instead of shooting the rays from the sun itself, we just shoot rays from the eye. So we just shoot here and let the material do the calculations of the scatter. So scatter is the word we use. Scatter is pretty much the direction the light is going to take after it hits a certain point, right? Certain point meaning hit anything at this point, right? And it could go here, and if it goes in this direction and the sky above, so it'll go in infinitely above, will return the color of the sky. So this point here is going to be the color of the sky. And if this point actually bounces here, we're going to sample the color of the ground, and this is going to get the color of the ground with some attenuation, of course. And If it shoots and goes into the light, then we'll sample the color of the light, which will, in our case, let's just keep it white. So this area is going to be white, and so on. So instead of shooting rays from the light source itself, we'll be doing shooting rays from the eye, so the camera point. Now, one important question you might ask is, where are the shadows? We haven't really defined shadows, right? In theory, at least. And we really don't have to define shadows. And that's the cool thing about doing a brute force path tracer or ray tracer, is we can actually have a depth value. So how deep you want the rays to go. So for example, this is going to be depth number 1, this ray, and this ray is depth number 2, and we can shoot it again, and this will be depth number 3, right? Now we can give a base statement in our recursive function. So this whole ray tracing application is going to be a recursive function. So when this ray hits a max depth, we'll just return the color of the shadow. So for example, if I shoot here, and let's just bring a black color and thin it out, and this ray hits here, right? And it bounces again, hits here, bounces again, hits here, bounces again, hits here, hits here, hits here, and this reaches a max depth, we return black color, and then we return black color, and then we return black color. So till this point, it's going to be black color. And even this point that hit here is going to get sampled this color, right? So it's eventually going to get blacked out. So just the byproduct of our direction calculation is going to be the shadow.